Let's try this Canadian Mathematical Olympiad 1972 problem. What is the maximum number of terms in a geometric progression with common ratio greater than 1, whose entries all come from the set of integers between 100 and 1000 inclusive? So basically what this problem is asking is how long is the longest GP in the set 100, 101, and so on until 1000. So let's try to find some long GPs that we can find, and then we try to prove that it's the longest. So the first thing that comes to mind might be to take 100 as the starting number for the GP, because it makes sense that if a GP is long, it must start early, right? But we'll kind of see that that's not the case. Let's say 100. Let's say we have r equals 2. Then we have 200, 400, 800, and it ends there, which is quite short. But how about we have rational common ratios? Like, let's say we want it to be greater than 1, so maybe we try 3 over 2, which is the smallest possible ratio if the denominator is 2. And let's see if that works. Let's say r is 3 over 2, then the next term would be 150. Then it would be 75 times 3, which is 225. And then we're stuck, right? Because 225 doesn't have a factor of 2. And so there's kind of a constraint here. The denominator of the common ratio would affect the length of the GP as well. It's not just the first term. So in that case, 100 is not really a good candidate. It has relatively few factors. We can find one with more. Maybe we can try 128, because it's a power of 2, which means that we can multiply r by many times. So let's try 128, and then we take the same ratio, 3 over 2. So the next one would be 64 times 3, which is, I'll just write it 64 times 3. And then the next one would be 32 times 9, and then 16 times 27. And then 8 times 81, which is 648. Can we go further? Yes. Next one is 4 times 243, which is 972, if I'm not wrong. Yep. Okay, so this is a really long geometric progression. It has 6 terms. In contrast, the one with 100, what we found was just 3 and 4 terms. So should we claim that this is the longest one? Let's try. Let's try and see if we can prove that this is the longest one. So let's say the first term is a, and the ratio is r, which is p over q. We are definitely sure that the ratio must be rational because it is the ratio between the second term and the first term, which are both integers, right? So here we assume that p is greater than q. The GCD of p and q is 1. And of course q is greater than 0, so I'll write it like this. So here we have a sequence of 6 terms. Let's see if we can break that record. Alright, let's see if we can find a 7th term. A 7th term would mean that it must be a times r to the 6, right? So if that's the case, we have a p to the 6 divided by q to the 6. But q and p are co-prime, so that means q to the 6 divides a. But not many numbers have a 6th power as a factor, right? Let's say q is greater than 3. If that's the case, then q to the power of 6 is greater than 3 to the power of 6. And this is 243 times 3, which is it over 1,000? Okay, no, it's not over 1,000. But this is 729. And if q to the power of 6 is greater than or equal to 729, and a must lie between 100 and 1,000, that means a must be equal to q to the 6, right? That means a must be equal to q to the 6. Otherwise, it's twice of q, at least twice of q to the 6, which is greater than 1,000 already. Okay. And of course, if we put q equals 4, then q to the 6 is obviously greater than 1,000. It's greater than 100, it's greater than 2 to the power of 10, so it's greater than 1,000. So there is no value of a, and hence no value of a. And hence, in this case, a must be equal to 3 to the power of 6. And the ratio must be p over q. Q is 3. So p must be greater than or equal to 4. And therefore the second term is 3 to the power of 6 is greater than or equal to 3 to the power of 6 times 4 to the power 4 over 3. But this is 243 times 4. Okay, this is still under 1,000. But the third term is obviously more than 1,000. So in all cases, q is greater than 3 does not work. Does not work as in it doesn't break the record of 6 terms. So that leaves with the case of q equals 1 or 2, right? Q equals 1 or q equals 2. If q is 1, that means r is at least 2, because r is an integer greater than 1, and if the denominator is 1, then it must be an integer, so it must be at least 2. But then we must have the GP must be a, 2a, 4a, and so on, where a is at least 100. So if a 7th term exists, a 7th term must be at least 100 times 2 to the power of 6. But this is 6400, which is greater than 1000. So that's a contradiction. Okay, so we're left with q equals 2. So R equals P over 2. So P is at least 3. And we must also mention that from our previous logic, we also have 2 to the power of 6 is a factor of A, right? So A must be 64, which doesn't happen. 128, 256, 512. It can only be one of these 4. Except 64. So it can only be one of these 3. So that isn't a very hard case. So we just say if A is 128. We've already checked just now that with P equals 3 we get 7 terms. And for larger P's, it will get larger very quickly, so there won't be, 6 terms. There won't be 7 terms. So this is the case we have already checked. If A is 256 and we must have the 7th term, so A times P, A times P to the 6 over 2 to the 6. This term must be less than 1000, right? But of course, this means that A 256 over 2, okay, so A is 256 over 2 to the power of 6 is 4. So we have this thing, or this, which doesn't hold, right? Because P is greater than or equal to 3. But 3 to the power of 6 is 729. So this is a contradiction again. And for the last one, it's even worse, right? So 512 P to the 6 over 2 to the 6 is less than this. We have that P over 6 is less than 1000, not only divided by 4, but divided by 8. So it's a even smaller constraint, so that's a contradiction as well. So after all of this, we have that the 7th term can never exist. And therefore, the longest GP in the set would be, the longest GP has 6 elements. And that's the answer for this problem. And the proof we have just done.